So, welcome to this week's lecture. Today, I will discuss first we'll discuss statistical thermodynamics, or the concept that connects the atomistic understanding of materials to the thermodynamic principles. See, for example, we have so far discussed the macroscopic thermodynamic parameters such as, for example, U, volume, internal energy, volume, entropy, then mole number and of species, then for example temperature, pressure, right, even heat capacity CV or CP. So all these were macroscopic description of macroscopic thermodynamic description, and basically these are all macroscopic measures of materials, right? However, when we talk of materials, we talk of an atomistic description, where atomistic description of matter, of materials, where we tell that any material is composed of atoms, right? Any material is composed of atoms or molecules, and we also tell, for example, when there is an atom, then that atom has a position in space. That is, I have to define some coordinates. For example, if I tell, say I consider a monoatomic gas, then what I'll do, I'll first consider that it is composed of these atoms in a container. We'll consider a container maybe. Inside this container, we'll consider a bunch of molecules, gas molecules. And when you consider these gas molecules or gas atoms, because these molecules are basically at a single atom, because it's a monoatomic gas. For example, helium, so helium or argon, neon. So these inert gases basically are monoatomic. So, and each atom, when we describe, what we tell, its mass. So when we describe a monoatomic gas in atomistic description, if I give an atomistic description, then I specify mass of each atom, and that mass of each atom, say let us consider it as m. Then I specify the atom's position in space with respect to a coordinate system, position in space. So position in space requires 3 coordinates, right? X, Y, and Z. It's a three-dimensional. It is a three-dimensional description of matter, right? We are three-dimensional. So basically, we have to use 3 dimensions to describe an atom of a monoatomic gas, right, in a container, and to specify the position of that atom, that atom, we require the position coordinates X, Y, and Z. Similarly, the gas atom, for example, is moving around, right? It is moving around. It has a kinetic energy, translational kinetic energy. If you remember, in a previous lecture, I have talked about translational kinetic energy, vibrational kinetic energy, rotational kinetic energy. So think the translational kinetic energy again. If I have to describe the translational kinetic energy of an atom or a molecule, what I have to specify? I have to specify the velocity or momentum. So if velocity of if I have to describe its velocity, so for each atom I have to describe its velocity. So if I have to describe velocity v, okay, and if for each atom if I have to describe that velocity v is a vector, so it has again, position is a vector, so it has three coordinates, right? X, Y, and Z. Again, velocity v, it's a vector. It has three coordinates: Vx, Vy, and Vz. And once we have specified all of these, I can basically write the translational kinetic energy So if I can basically write the translational kinetic energy, which is half m Vx square plus half m Vy square plus half m Vz square. Now each atom, now this is the most important part, that the most important part in atomistic distribution is that each atom has its own position in space, each atom has its own velocity in space defined by the Vx, Vy, and Vz. And the atoms, say for example, if this is gas atom and these are enclosed in a container, then these atoms will be colliding with the walls of the container and will change its velocity. It will change its velocity direction. So, but if I have to now equivalently describe something like an internal energy, I require some sort of an average, okay, of over this entire collection of atoms. And this entire collection that I am talking about is a very large collection of atoms. For example, if it's just 1 mole, if I think of 1 mole of gas atoms, what I am describing is like 6.023 into 10 to the power 23. As you know, this is Avogadro number of atoms. So it's a massively large number of atoms that are occupying, even if I am considering only 1 mole of atoms. If we are considering a container that contains 1 mole of gas atoms, or monoatomic gas atoms, I have so many atoms, and each of these atoms has a unique position in space, it has a unique velocity, and now we have to find out how we can calculate an average velocity, and that average velocity will basically give me an average translational kinetic energy, assuming again these atoms are not interacting. If they interact, then we have to basically also discuss the interaction force between them. However, when you look at the macroscopic thermodynamic description, we talk about an energy. That energy is like the total energy of all these atoms that are enclosed in the container. We talk about its volume, so which is basically described the volume of the container itself, right? When a gas is enclosed in a container, then the gas is spread all over the container, and as a result, the volume of the gas is nothing but the volume of the container. And then we have to think of right, the mole number is like 1 mole, but 1 mole contains so many atoms. And finally, when we do all of these, when we do all this analysis, I need to connect this U and V, and we will get some very easy constitutive law. Say for example, PV equals to nRT, where n is the mole number, you can call it capital N, it is the mole number, R is the universal gas constant, T is temperature, V is volume, and P is pressure. Now this is a macroscopic equation of state. So how do we arrive at this? From this microscopic world of so many atoms, each atom having its own position and velocity, is what I will describe. And I will also describe, say for example, we have defined something called entropy. I have described something called entropy, right? Entropy S, with a function of U, V, and N. Again, so entropy S again is a macroscopic thermodynamic parameter, which is a function of macroscopic extensive variables like internal energy, volume, and mole number, Then we also told how S is connected to, say for example, CV or CP, that is the heat capacities at constant volume or constant pressure. What is the connection between them? That also we discussed. And then we discussed also, for example, how is S related to heat transfer, and we have described, for example, ds is greater than equal to delta Q by T, right? So we have described various thermodynamic means various macroscopic parameters to describe all these macroscopic quantities. Now, how is S, for example, related to, what is connection of S, or what is the connection of C, heat capacity, CV or CP, to the position and the velocity, or more precisely the momentum, right? We have M also of each atom, and these we are taking on a large, we can think of these pointed brackets, that the enclosing brackets as some sort of an average of the collection of atoms, right? This average of the collection of atoms, how are they related to this S or heat capacity, is what we have to explore, and that is why these lectures. So these lectures will basically give you elements of a very important idea, and that is called statistical mechanics. This will give you statistical, obviously statistics is required when you have a large population of something, right? In this case we are dealing with a large population of particles. So this will basically tell you a statistical mechanical description of matter. So this is a very basic means introduction. This is not like a course on statistical mechanics. So we are looking at the elements of statistical thermodynamics that are useful to connect. So we are looking at the elements of the statistical thermodynamics that are useful to connect these macroscopic quantities to the microscopic quantities, like the mass of atom, or the position of these atoms in space, and then different species type, right? Atomic species type, and all of these we want to give so that's why we are giving a statistical mechanical description of matter, which relates microscopic quantities. Basically microscopically, if I can define some quantity, some averages, these microscopic averages will be related to macroscopic thermodynamic parameters. Right? So this is what we are going to do. Now we know, so first thing that I can start with is like equipartition theorem, right? Equipartition theorem. We have told that there is a relation between temperature of a system and its average energies, right? It gives you a relation between temperature of a system and its average energies. Every atom of an inert noble gas, okay, that inert noble gas you can think of like it is the closest to the approximation of ideal gas, right? Inert noble gas, which is monoatomic, and which is also not as much interacting. So these inert noble gases are the closest approximation to this concept of ideal gas, right? Ideal gas is a concept that we have drawn. Basically, this ideal gas concept gives you a very simple equation of state. It also gives you a very simple non-interacting description of these atoms. So when we tell that the atoms are non-interacting, right, there is only thing that these atoms are doing is these atoms are moving with a velocity, and this is occupying some position in space. And if you want to, this idealization can be achieved in reality if we consider an inert noble gas at certain temperatures and pressures. Now, there what we are telling in the equipartition theorem is every atom of this inert noble gas that is in thermal equilibrium at temperature T has an average translational kinetic energy which is 3/2 kBT, right? So where kB is the Boltzmann's constant and kB is related to the gas constant by R by Na, which is R is the universal gas constant divided by the Avogadro number, which gives you kB. So every atom of an inert noble gas that is in thermal equilibrium at temperature T has an average translational kinetic energy which is 3/2 kBT, right? And this is something that when you start with that, this is where first the molecular interpretation or atomistic interpretation of temperature of energy comes in, right? Because we are talking about kinetic energy. That's translational kinetic energy is the if you think of an ideal gas or an inert noble, which is again an example is an inert noble gas, the closest approximation to ideality. So in that case, what we are ignoring is the interactions between the atoms. We are ignoring the interactions between the atoms. We can ignore the interactions between the atoms, and we are telling that the internal energy of this collection of monatomic gas atoms is basically coming from its translational kinetic energy, and this translational kinetic energy is 3/2 kBT. Now, if I have to basically show that, okay, this indeed is so, that means the kinetic energy, which is half mv bar square. Now, V bar, when I am talking about V bar is an average of over the collection of these atoms. So, or collection means you can call it an ensemble average or the average of the collection. So, it's an average velocity. It's an average velocity of a collection of atoms, and the average is taken over a very large number, and that very large number, as I told you, for example, is like the Avogadro number, which is 6.023 into 10 to the power 23. It's a very large number of particles or atoms, and over which, so each atom is moving with some velocity, and we are taking an average of all of these, and we are calling it from there only we are calculating the average translational kinetic energy, which is half mv bar square, which is again in terms of the components half mv vx bar square, vy bar square, and vz bar square, right? So you have vx bar square, vy bar square, and vz bar square, which basically has to be 3/2 kBT. Now, if I want to basically understand it, I can think of a one-dimensional, say I have a three-dimensional description of matter. So this is my y-axis, this is my x-axis, this is my z-axis. So this is z and y, and this is y. Now think of there is this gas molecule, hypothetical gas atom, which is moving, and this is the wall of the container, right? We are talking about a wall perpendicular to the motion of this atom. This atom is moving in one dimension along x direction. Now it has some velocity vx, and when it hits the wall, it has a velocity which is minus vx, right? So, and the volume can be described by, so if I have taken this container, okay, or this box, which has this dimension delta L, this delta L is the dimension that is along the, so basically I will do one thing, I will make a little correction here. I will tell that this is my, so if I look at this delta L, so I can think of this as my x-axis, this as my y-axis, and this as my z-axis, and so this is the positive Vx and this is minus Vx, right? So basically an atom moving towards the wall is moving along negative x direction, and then when it hits the wall, collides with the wall and comes back, then it is moving in the positive x direction, right? We can tell any of these, right? We can specify any of these directions. So basically it's a one-dimensional problem. So we are looking at positive x direction and negative x direction, right? So we are looking at the direction towards the wall and direction away from the wall, but in the same, along the same x-axis. Now, but we are also considering this cross-sectional area. See, this analysis, the analysis that I am trying to present, is a very, very simple analysis, and this analysis, although we will do it in one dimension, along one dimension, we will extend it to 3 dimensions. So I have this total volume, which is nothing but this delta L times the cross-sectional area. So this is delta L times the cross-sectional area. A is the cross-sectional area, right? So this is the cross-sectional area that I am talking about, which is basically perpendicular to delta L, right? This area is perpendicular to delta L. So this is the cross-sectional area of the wall, right, that I am talking about. And this is the same cross-sectional area that the atom is experiencing. So this is basically delta L times A. And I am telling the total number of atoms, NT is the total number of gas atoms or gas molecules, is nothing but N is the mole number times Avogadro number, right? Mole number times Avogadro number gives you the total number of atoms, total number of gas atoms. Now, what we are telling is, over a time period delta t, so this atom is moving over a time period delta t, so this is moving here, and then it comes back, and then again maybe there is a wall on this side, and again it moves back and forth. So over a time period, a small time period delta t, on an average, there will be, so now we are looking at a collection of atoms. Let's think of this total number of atoms here. So on an average, if you think of all these gas molecules colliding with the wall and coming back, then NT by 2 atoms are moving towards the wall. Half of the atoms, half of the total number of atoms is moving towards the wall, and half of the total number of atoms is moving opposite to the wall, right? So half of the total, so on an average, over some time period, we are telling that NT by 2 atoms, NT is the total number of atoms, NT by 2 or half of the population of atoms is moving towards the wall, and half of its population is moving opposite to the wall, right? And again, as I told you, it's an average velocity. The average velocity, now this is the definition that we are thinking of, root mean square velocity, right? It's a mean, so we are looking at like a root mean square measure. So that means mean square means we are talking about Vx square 1 plus, so basically if I look at the Vx average, so basically this is like this. So if I look at Vx average, I can think of like this, Vx average is equals to root over of, so for each atom, Vx1 square plus Vx2 square plus dot, so Vx NT square by the number. So this can be N, which is nothing but NT. So in this case, it is NT. So it's a root mean square. So that means it has to be divided by NT, and then we are taking the square root. So that basically defines my root mean square average velocity, RMS. So this is RMS, root mean square, RMS measure, right? Root mean square measure of the average velocity along x direction, or the x component of velocity. Root mean square x component of velocity is defined by this. So you have the the root mean square velocity along plus x, which is Vx bar, and then there is also root mean square velocity along minus x, right? So you have a velocity towards the wall, a velocity away from the wall, right, after colliding. So this is along plus x and one is along minus x. And m, let us assume m to be the mass of each atom. Now, since it's a monoatomic gas, and it's a say for example neon gas or argon gas, then it is like basically all atoms are argon, right? So they are all identical atoms in terms of the chemical nature, and they have the same mass. Okay, so m is the mass of each of these atoms, right? Now, if you think of that, Vx bar is the root mean square velocity along the plus x axis minus Vx bar is the root mean square velocity along minus x. Then the change in momentum. So we are assuming that the collision is perfectly elastic. That is, it does not lose any velocity, anything. It just or momentum. It just goes and hits the wall. The gas atom goes and hits the wall, and then it comes back with the same velocity, means same magnitude, but in the opposite direction. So then the change in momentum is nothing but mv x bar minus mv x bar, right? Because this is minus, there is a minus vx bar and plus vx bar, so this becomes 2mv x bar, right? The change in momentum is 2mv x bar. Now if I look at rate of change of momentum, right, if we think of Newton's second law, what we look at? Rate of change of momentum, which we will relate to force. Now rate of change of momentum is 2mv x bar by delta t, because we are looking at we are analyzing our time period of delta t, right? In this interval, all this is happening. So over this time period, the rate of the change of momentum is mv x bar, 2mv x bar, and then if I divide by delta t, then what we get is the rate of change of momentum, and that is nothing but the force according to Newton's second law, right? It is nothing but the force which is equal to from Newton's second law. Now if you see this very carefully, if you look at the force, you first have to understand what is this volume. And now, as I want to tell you, delta S, if you look at delta L, which is the distance, right, is the linear distance travel, then delta L is basically velocity times time, right? Distance equals to velocity into time, right? Delta L equal to Vx bar delta t. Thus, the volume can be written as A Vx bar delta t. So, what we did is volume was delta L times A. Now, delta L I am writing in terms of the root mean square velocity Vx bar times delta t times, right? So, this becomes Vx bar delta t A. So, I have just rearranged, I have written it as A Vx bar delta t, right? So, now you have A Vx bar delta t, and we have, if I look at force, I will consider only half the molecules, right? So I am considering half the molecules is moving along one direction and the half the molecules are moving on the other direction. So if I am thinking of a force exerted by the atoms on the wall, then I am considering only half the molecules that are moving towards the wall. So then we have this nt by 2, and if you see 2 mvx bar by delta t, 2 mvx bar by delta t is, so I have a by delta t missing here, is my rate of change of momentum. And if you see, this A Vx bar delta t is volume, and this is volume by volume, so I have just written it here. And you have this nt by 2, right? Nt is the total number of atoms. So if I have that, then the force exerted per unit area, which is basically the pressure on the, is F by A, which is, if you see, you have Vx bar here and Vx bar here. So this becomes Vx bar squared, and then M, and 2 cancels. So you have mvx bar squared, and then you have nt by v. So this 2 and this 2 cancels, right? This 2 and this 2 cancels. This and this cancels. So you have this term and this term. Now delta t and delta t cancels. So you have A is there, but P is, what we are considering is P, which is force by area, which is basically, this is nothing but pressure. Pressure is forced by area, forced by the cross sectional area, which is mvx bar square nt by v. Correct? So nt by v. Nt by 2 is the total number of atoms that are basically exerting the force on the wall, right, at any point of time, because half of it is moving towards the wall, creating the pressure on the wall, and then it is moving back, right, it is moving away from the wall. So now nt, as we have discussed earlier, is n is the mole number. So nt equals to n times the Avogadro number, right? Na is the Avogadro number. So then what we can write is P, and here there is V. V is volume, right? It is the volume. Volume of the which is basically A Vx bar delta T is what I have expressed, but it is also delta L times A, right? which is nothing but Vx bar delta T by A. Now, if you see, you have this volume here and the total number of atoms here. So, if I take volume on this side, then it becomes PV equals to Mn N. Why? Because there is a Nt which is equal to N and A, right? So, M is the mass, N is the number of moles, and then Na is Avogadro number, and this is Vx bar square. So, PV equals to this expression. P is a average, it means on an average or macroscopic thermodynamic quantity. V is another macroscopic thermodynamic quantity, and see, this is the microscopic quantity. This is another microscopic quantity. This is mole number, but it is multiplied by the Avogadro number, which is the Avogadro number of molecules for 1 mole of atoms. Then you have, and we know that macroscopically the equation of state can be written as PV equals to nRT, which is nothing but MNNA Vx bar square, and Kb here is, if I define Kb or Boltzmann's constant as R by Na, which is universal gas constant by the Avogadro number, then what we get is mVx bar square is R by Na into temperature, right? If I compare this equation, which is the equation of state, so this is my equation of state for the ideal gas, and this we got from the microscopic description. If we relate them, what we get is that PV is nothing but or mVx bar square, mVx bar square, right? PV is equal to nRT, PV is equal to also this. So if I equate this, nRT equals to MNNA Vx bar square, I can write this. So nRT equals to MNNA Vx bar square, and N and N I can cancel, and I have mass here, Na here, R and T. So if I take R, so if I have T here, and instead of R I will use R by Na, because I am taking this Na this side. So if I take that this side, then I will remove Na here. So what happens? Rearranging, what we get is mVx bar square equals to R by Na T, which is nothing but Kb, Boltzmann's constant, right? So mVx bar square equals to R by Na T or Kbt, right? So we have mVx bar square. Similarly, likewise, if I extend to 3 dimensions, then what happens? We get, since V bar square, right, on an average, that this is like a root mean square velocity, right? Root mean square velocity, which has all these components. So root mean square x component of velocity, root mean square y component of velocity, root mean square z component of velocity, and the probability. So basically, since there is no anisotropy here, there is no anisotropy movement along each direction, whether it is along x direction, whether it is along y direction, or whether it is along, say, x is this and y is this. So this is x direction, this is y direction, and this is z direction. And if we tell that the probability of moving along any of these directions is equal, then Vx bar equal to Vy bar equals to Vz bar, right? That's what I am telling. Because there is no anisotropy, there is no preference along one particular direction, right? So it's all equally probable. If it is all equally probable, Vx bar and Vy bar and Vz bar, these are the components of the root mean square velocity. The root mean square velocity components are all equal, then V bar square is nothing but, according to this relation, V bar square is nothing but 3 Vx bar square. Now, if it is 3 Vx bar square, we have already proved that mVx bar square equals to Kbt. So, mVx bar square equals to Kbt, and average energy of each atom, for example, is nothing but half mVr square, V bar square, which is nothing but equal to half m. Now V bar square, I have seen V bar square is nothing but 3 Vx bar square. So half m 3 V x bar square, which is basically 3 by 2 mv x bar square, but we have proved that mv x bar square is nothing but kBt. So this is kBt, so this is 3 by 2 kBt, right? So basically the average energy per mole is basically, so this is like per atom. So if I think of per atom, this is like energy per atom, which is 3 by 2 kBt. Now U per mole is Na times E, which is Na, which is the Avogadro number, times 3 by 2 kBt, which is equal to 3 by 2 RT, since R equals to or since Kb equals to R by N, right, or R equals to Na times Kb, right? So we get this. Now we know this description, we understand this, and we have also shown it, but we did not go through all the detail here, but we can immediately now realize that there is this molecular interpretation of internal energy, which I have described a little bit previously, but here we give you some sort of a derivation or description. It's not a derivation as such, the derivation is much more involved, but it at least gives you the connection between this 3 by 2 kT and the on an average the kinetic energy, the translational kinetic energy. Now what about entropy? Now entropy, as we have seen, is entropy is increasing for an irreversible process. Entropy of an isolated system increases when the process is irreversible, otherwise the change in entropy is zero, and all of this stuff we have talked about. But what is the microscopic understanding of entropy, right? So we want to again give this connection between the microscopic world of atoms and the macroscopic thermodynamics. In macroscopic thermodynamics, S is a very, very important quantity, right? Entropy is a very, very important quantity. We talk about the second law, which is nothing but del Q. We can write it as del Q reversal equal to TdS. Then we talk about Clausius inequality, and we also talk about the different properties of entropy, right? Entropy vanishes at absolute 0 Kelvin. Then entropy is a monotonically increasing function of energy, which is differentiable, right, and continuous. But what about the molecular interpretations, right? So here we will try to describe that in terms of arrangement or configurations. So let us look at different types of atomistic configurations. Let us think of this very simple description of 4 A atoms, and you have 4 boxes, right? You have 4 boxes here, box 1, box 2, box 3 and box 4. Now I am talking or considering 4 A atoms. All of these are identical or indistinguishable, and I am telling that how many ways I can arrange these 4 A atoms among these 4 boxes. So the answer is I have 4 boxes and I have 4 atoms, and since these are indistinguishable, there is only one way you can put these 4 atoms, right? There is only one way. So since they are indistinguishable. Similarly, let us think of B atoms. Now, so basically I am talking about 2 different atomic species. So I have one is A is like copper, and another is say B, which is like nickel, and or say neon and argon. So something like that. Okay, so it can be a gas mixture, it can be solid, it can be liquid. So, but these are 2 different atomic species. But if I consider B alone, and if I consider the same box with these four placeholders, so I have this one placeholder 1, placeholder 2, 3, and 4, and I have 4 B atoms, all of which are identical, right? All of which are indistinguishable among themselves. Although A and B can be identified, B alone cannot be identified, or A alone cannot be identified, or basically they are all identical. One A cannot be distinguished from the other A, one B cannot be distinguished from the other B, but A can be distinguished from B, right? So you have B atoms and A atoms. Even for B atoms, the same idea holds, right? For 4 B atoms, you can only arrange in one way if they are all identical. So whether it is A atoms or B atoms, you can arrange only in one way, right? If we are only considering one of these atoms, we are considering 4 A atoms or 4 B atoms, right? Then the arrangement, there is only one way to arrange these atoms among these 4 placeholders. However, as I told, A is indistinguishable, right? It is distinguishable from B. We can distinguish A from B, right? A and B are different. Distinguish means I am telling A and B are different. Now, if A and B are different, and I have two A atoms and two B atoms, think about it. Two A atoms and two B atoms, and look at this description. So I have like two A's on the top, and then two B's at the bottom, and then two A's this way, and two B's on the left side, and two B's on the right side. Then I have the reverse thing, right? BA, and all of these that we have drawn. So BA and AB, or AB, BA, and BB on the top shelf, and AA on the bottom shelf. So these are the four placeholders, and I have found that there are 1, 2, 3, 4, 5, 6. So four placeholders, two A atoms, two B atoms, A atoms and B atoms are distinguishable. We are finding 6 ways to arrange, right? 6 ways to arrange them. Right? So there are 6 ways to arrange them. Now think of this. If I have all atoms that are distinguishable, they are all different species. Means A is different from B, which is different from C, which is different from D. Now you have A, B, C, D. Now this A, B, C, D, these are 4 different species, and these we have to arrange among 4 placeholders, 4 empty placeholders. Then there are 4 factorial ways, or 24 ways to arrange them. Okay, so find out why. So you have, like, if you put an A here, so basically I can tell you this way: A can be placed in any of the 4 empty placeholders. Then B can be arranged in 3 ways, right? In the 3 empty space holders. Means once I have placed an A, so basically I can place A in 4 ways, right? A can be placed in any of the 4 ways. These are all empty, right? A can be here, or A can be here, or here, or here, right? So if once I have placed an A, I cannot place the A, right? So A can be placed in 4 ways. So basically, if I tell there are 4 empty placeholders, so A can be placed in any of the 4 empty placeholders. Now you have remaining 3 empty placeholders. So B can only be arranged in 3 ways, right? Because the 3 remaining empty. So basically 3 remaining empty spots, right? Remaining placeholders. Now once I have arranged or placed B, then there are only two remaining, right? 2 remaining placeholders where I can placeholders that are empty, where I can basically take any of these 2, or I can put a C. Then I have only 1 remaining, right? 1 remaining placeholder for D. I can do it with starting with C, I can do it starting with B. You will basically get it the same type of arrangement. So you have 4 ways to put any of these 4 atoms, like 4 species. We have 4 distinguishable atoms. Remember, these are 4 distinguishable atoms. And we have 4 empty placeholders. Now, if A can be placed in 4 ways, B can be placed in the remaining 3 placeholders, and C can be placed in the remaining 2 placeholders. So you have 4 times 3 times 2 times 1, and that is your number of arrangements that are possible, right? 4 times 3 times 2 times 1. which is basically nothing but 4 factorial, right? This is nothing but a 4 factorial number of ways, right? Because n factorial equals to n times n minus 1 times n minus 2 times dot dot dot, then 3, 2, right? That is n factorial, definition of n factorial. Now we have, as you can see, there are 4 empty placeholders and 4 atoms, and these are all distinguishable. Now since they are all distinguishable, A can be placed in or B can be placed in any of the 4 ways, then the remaining A can be placed in any of the 3 ways, and C can be placed in any of the 2 remaining placeholders, empty placeholders, and D can occupy the last one. So whichever way you start with, you will always end up with 4 factorial number of ways or 24 ways. However, if you look at the previous example, we could only see 6 ways to arrange them. Why? Because 2 A atoms are identical and 2 B atoms are identical, although A and B are distinguishable. So there are only 2 distinct, means if you think of that, A and B, these are the 2 distinct cases, right? Means I can identify A from a B, but I cannot identify A from an A or B from a B. And as a result, the number of ways have reduced to 6 from 24. If A, B, C, D, all of them were there and there were 4 boxes or 4 placeholders, then we have 24 ways. But if I have 2 A's and 2 B's, I have 6 ways. So this is where comes the idea of combination and the idea of arrangement of particles in different ways. And if I am looking at, if we are not considering the order of arrangement, then what this idea comes in is from statistics, and this is called combinatorics. And in combinatorics, we actually solve such problems, that how many ways I can arrange some red balls and blue balls among some 4 empty boxes. So many such combination, or 10 empty boxes, how many ways I can arrange a deck of cards, and all of these basically is in the field of combinatorics. And this combinatorics gives us an idea of number of ways of this different or distinct arrangements, and these arrangements basically give us an idea to interpret entropy. This is something that I will come to here. So for example, the problem that we are talking about, say what is the problem, which basically the problem here is statistical mechanical or statistical interpretation. We are trying to come up with a statistical interpretation of entropy, which is a macroscopic thermodynamic parameter, right? And we know this entropy is basically nothing but it basically gives a way, or entropy basically describes irreversibility, right? Entropy is always increasing. If the process is irreversible, if the process is reversible, the entropy, the change in entropy is 0. Now, when I am talking about statistical interpretation of entropy, remember we have moved away from that definition of entropy increasing and stuff, but we are looking at arrangements, we are looking at configurations. So somehow we will make a connection between them, and I think means the idea is that Boltzmann looked at this idea, and then he came up with a very interesting hypothesis, and that hypothesis neatly fits with the macroscopic thermodynamic description, right? So we'll try to describe that, how these configurations or these arrangements can basically give you this macroscopic quantity called entropy, or how are these connected. So that is the problem. The problem is first, but the problem can be now subdivided. So we have this problem of n1 elements of type 1, n2 elements of type 2, n3 elements of type 3, and nk elements of type k. So nk elements of type k. So it can be like k species. Think of k different atomic species. Now k different atomic species are there, right? So one type 1, type 2, type 3, type 4, like these are like different types of atoms, and we have total n positions or n placeholders. Now each type is distinct or distinguishable from the other. That means type 1 is distinguishable from type 2, type 2 is distinguishable from type 3, and so on. But among n1 elements, so we have these n1 atoms of type 1, say, these n1 atoms are indistinguishable or identical, and n2 atoms are indistinguishable and or identical. Now, when I am looking at this arrangement, we are also telling that these n positions are there and these elements are there, and there is this additional constraint, and the constraint is this, that sum of all these elements, that the number of these elements, so n1 of type 1, n2 of type 2, n3 of type 3, and nk of type k, so sum of all of these add up to the number of placeholders that are available. The number of empty slots that are available is n, and n1 plus n2 plus n3 plus dot dot plus nk is nothing but, right? So that is the constraint, right? That is the constraint that we have, and we want to find these arrangements, right? These different arrangements. That's the entire crux of the problem. Okay, so for that we will define something called a macro state, and so we will define something called a macro state, and we will also define something called a micro state. Okay, so in statistical thermodynamics, right, in statistical thermodynamics, where we deal with the large number of particles, like large number of atoms, large number of molecules, then it gives you probable states of particles in a system. Probable states means probable arrangements or probable configurations of particles in a system. What are the different probable configurations? Now, macro state basically tells it is very much identical to the state in macroscopic thermodynamics. When we describe a state in macroscopic thermodynamics of a simple system, what we use, we tell that it has this type of internal energy, it has a fixed volume, or fixed mole number, and we tell that this is the total internal energy of the system and stuff, right? So in macro state, basically you will see that it is very much equivalent to the state the macro state in statistical thermodynamics. I'll give an example. It is equivalent to the state that we define in macroscopic thermodynamics. So macro state is defined in statistical thermodynamics. Now we will find this, obviously we have to find a connection between them, but I am just telling you that this macro state will basically be equivalent to the state that we define in macroscopic thermodynamics, right? Like in simple systems, it is like we define it using some U, V, N. Very similarly, macro state is described, right? But micro state, now this is the interesting part, micro state denotes the state of all particles. So it denotes all the particles, it denotes the state of each of these particles present in the system. So it denotes the state of all particles in a system. That is what is described by micro state. So let us look at an example. Think of an isolated system. So you have an isolated system comprising of a gas occupying a given volume V at equilibrium, right? So isolated system comprising of a gas occupying a given volume V, right? So it's basically a gas in a container, right? And it is at a given volume V at equilibrium. So it's an isolated system. So some of the internal states are already defined, right? There is an isolated system means it does not allow any heat transfer or mass transfer, and we have this gas which is occupying a given volume, and it may be in some thermal equilibrium, or it may be its own. There's maybe some the constrained equilibrium we can describe. Say, for example, we can give a temperature, we can give a pressure. Okay, already we have given a volume to the gas. So that basically describes this macro state. That is an example of a macro state, right? So we are thinking of an isolated system that contains a gas and a given volume V, and that is the macro state, right? This is at equilibrium. But now if I have to define the micro state of this gas, then we have to define position and velocities. These are positions and velocities of all gas molecules within the system at any instant of time. So there may be, that means there will be a large number of microstates. So basically a macro state, which is an overall outcome, which is like some gas occupying a given volume V at equilibrium, and that gas has lots of atoms, right? It's like an Avogadro number of atoms or more than. So if I have 2 moles, like 2 into Avogadro number of atoms, and all these atoms, we have to specify the position and velocity at any instant of time. And think of this, when I am observing a macro state, the macro state passes through many micro states, right? Many instantaneous micro states are there, and all of these micro states average is what is going to give you the idea of macro state, right? So that is the idea. So for example, we can think of again microstate and macrostate if we again come back to statistics and the problem of counting, right? See, when we talk about combinatorics, the number of ways of arranging stuff, or number of configurations possible, and number of arrangements with a constraint or excluding repetitions and stuff, then what we come back to is the problem of combinatorics, or in statistics, and we call it this is statistical because we are dealing with a very large number of outcomes, right? But even if we consider some slightly smaller number of outcomes, and we can consider the problem of deck of cards or dice or a coin, then basically many of these things, means many of these ideas of microstate, macrostate becomes more and more clear. Say for example, so I'm just giving you this example of use 2 standard unbiased dice. Unbiased means if you have biased dice, then there is a possibility that, see, in a dice you have 1, 2, 3, there are 6 faces, and each face is labeled with like 1, then 2, then 3 to 4 to 5 and 6, right? So 1, 2, 3, 4, 5, 6 are the labels on the 6 faces. Now if I roll a dice, if it is an unbiased dice, there is an equal probability of 1 by 6 for getting either 1 or 2 or 3 or 4 or 5 or 6. However, if it is biased, then there might be a little more probability to obtain a 6 or a 1 than 2 or 3 or 4. Means I'm just talking about one example of bias. So basically we have to make sure that the dice that we have are unbiased, right? So there is an equal probability of obtaining any of these, like 1, 2, 3, 4, 5, 6. So this is the dice that one example of a dice. And so we take 2 of these, standard dice, and then we roll them, right? We roll them, and this rolling is nothing but the experiment that we are doing. So we are doing, and the outcome of this rolling is something that we are looking at. That the outcome is what is going to define the state. So the outcome in the previous case was the isolated system in equilibrium having a volume V, containing a gas with a volume V, right? So that was the outcome. So here the outcome that I am talking about, I can think of an outcome. We have these experiments. The experiments is rolling these 2 unbiased die, right? And we also know that you have 1, 2, 3, 4, 5, 6. These are the labels that are on each face of the dice and of both dice, right? So now if that is so, then if I tell the sum of numbers on both die faces gives you, so we have these both die, and we are telling that the sum of numbers is given. So for example, a sum 8 is given. So if I telling that sum 8, so the experiment should have an outcome of 8. How many ways I can roll the dice? Now this outcome of 8 is defining the macro state or the state, right? The outcome of volume V is defining the macro state. So exactly the sum 8 is the macro state. So the sum of the numbers on these faces of these 2 dice should add up to 8. Now if I am looking at that, how many ways you can get 8? So 8 is the macro state, or 8 is the outcome that we are looking at. But how many ways we can are basically going to define my microstates, right? How many ways we can is going to define my microstates. So if you look at that, so if you look at the how many ways it is going to connect my microstates, then you will see that if I have to get a sum of 8 for this 2 dice roll, then basically if dice 1 has a number 2, then the dice 2 should have a number 6. If the dice 1 has number 6, then the dice 2 should have number 2. Similarly 5, 3, 3, 5 or 4, 4. So these 5s, there are 5 possibilities or which will give rise to a sum of 8. There are only 5 possibilities that will give rise to a sum of 8. And sum of 8, that the sum of the outcomes of this dice roll, that sum of whatever is the level on the dice, that sum should add up to 8, that is the macrostate. But there are 6 microstates that will give the outcome of 8, right? So now you can understand the microstate is the instantaneous description, and over all microstates we have to choose over so basically one macrostate will pass through several microstates. These microstates are telling that this macrostate is possible, right? So sum of 8 is the macrostate, and there are 5, 1, 2, 3, 4, 5 microstates that basically gives you the macrostate, right? So we will describe this further in the next lecture. Okay, so I am stopping it here now, but I will, in the next lecture I will continue with this idea.